Swayam Prabha. Digital India. Educated India.
Hello. We looked at calculation problems in geometry. Now we look at that in mechanics. So, we already discussed there are three ways to look at mechanics, static and dynamic equilibrium, not just force balance and Newton's second law, other ways. Today we look at how these things come about from calculus of variations. Okay. Now let us look at a mechanics problem which is a beam. Let me get a pen. Oops. Okay, it is going back. Okay. Let us look at a beam problem. Okay. A beam that you are all familiar. When you have a beam, let us say I take a beam simply supported. So, there is a hinge. Now, if there is a force acting on it or forces, does not matter, any number of forces, okay, it is going to deform in some way, right. So, now we call this function W of x, transverse displacement, where x goes like this, x equal to 0 to the L. So, let us say this total length is L. Now, this beam can take a number of shapes as deformation, but it takes a particular one which satisfies this equation, which is a differential equation where the loading is q of x and there is Young's modulus E, there is second moment of area I, and W is our unknown function which is the deformation of the beam. And this one from your engineering mechanics courses you would have gotten it by doing either force or moment balance. Okay. That is a method 1 that we all learned, that when forces are balanced you get static equilibrium condition. Now, we will pose this problem differently using what we will call method 2, which is minimum potential energy principle. So, what does that mean? We have something called potential energy, which we write P E for us is potential energy. Potential energy. Okay. This potential energy is a combination of two things, and one is the strain energy. Okay. This is the what we denote by SE, which is the SE is strain energy, that is the deformation energy stored in an elastic body, strain energy. And then we have minus work done by external forces, and normally we write it as plus work potential. Okay. So, P E equal to potential energy, which is equal to strain energy plus work potential, where this work potential is the negative of work done by only external forces, work done by the external forces, okay, not the internal forces, and that is the important distinction here. We do not need to worry about forces that are inside or internal forces, we only look at external forces and how much work they have done, negative sign, that becomes work potential. Strain energy, which is basically area under the stress strain curve for a body, okay. That in the case of a beam is given by this expression, and we get a functional, as you can see, from 0 to L, that is 0 to length of the beam L, we have a functional which is strain energy functional, and then work potential functional. Both are put together if minimize potential with respect to W, and that gives you the static equilibrium condition which we had in the previous slide. So, this is obtained with force and moment balance, whereas we can get this same equation by minimizing the potential energy with respect to W of x. This is what minimum potential energy principle says. In other words, while the beam has a number of, okay, so let us draw some of them. This beam can actually deform like this, right. Instead, it is deforming to a particular one because that particular one minimizes the potential energy. As you change W of x, this expression is going to change. There is W here and second derivative of W here, right. There is W here, the second derivative of W, and as you change W, the value of potential energy is going to change. That W will be chosen by the beam which minimizes this potential energy. That is what this second method says. There is a third method now. First one was force and moment balance, second is minimum potential energy, third one is what we call principle of virtual work. Virtual work is not real work as it is implied in its name. What it says is what is put here in words. Okay. It simply says that internal virtual work is equal to external virtual work. What is internal virtual work? It is the work done by the internal forces when you imagine a virtual displacement. Okay. What you do is, let us say we have a beam, let us say that our beam that is pinned at both ends and fixed at one end, and then what we call simply supported condition is a slider condition there. Let us say this beam has taken this particular shape under some loading. Okay. Now, what you do is you imagine a virtual displacement around it, okay, small perturbation, what we called variation earlier, okay, that color has not changed, okay, a small perturbation around it. Okay. So, that is the virtual displacement, that is distance between whatever that is there to here, that is your virtual displacement which we are denoting as delta W. Okay. That is a virtual displacement vertically, that thing. Okay. So, this is the virtual displacement. It is virtual meaning it is not real, you just imagine, it is just a thought experiment. You know that the beam has already achieved equilibrium, but you want to find what that is. So, you imagine that around that there is virtual displacement, then you calculate the internal virtual work and external virtual work. Internal virtual work is the work done by the internal forces over the virtual displacements, and external virtual work is the external forces work over these virtual displacements. Now, when these two are equal, that is what this thing says, principle of virtual work, and that also gives you an equilibrium equation which looks like that, okay, which says that this side is internal virtual work, this side is external virtual work, and this is true for any delta W x. Okay. That is a perturbation that we considered, right. The virtual displacement, something that we imagine that can be arbitrary, that means our imagination can be arbitrary for any of them. If this holds good, then the W that we have taken, the original W of x that we have taken, that is the static equilibrium solution. Okay. That is what this principle of virtual work says. Okay. It is a very profound principle, and Bernoulli was the one who thought of this way of doing rather than force and moment balance, and later several other people have developed. So, this statement which is very simple, internal virtual work equal to external virtual work, gives you the equilibrium equation which is same as what we have written over here with the force balance, or what we will get if you were to minimize energy, or what we will get if we solve this problem such that delta W is arbitrary, even then this equation holds, that is internal virtual work is equal to external virtual work. So, this is a very important consequence of calculus of variations. Okay. Again, to summarize, there are three methods: force or moment balance, and then principle of minimum potential energy, and then the principle of virtual work. Normally, when you do this with the first method, it is called the strong form. Okay. Strong form meaning that the the differential equation that you get for static equilibrium will be in the strong form, meaning that you have to usually will have higher derivatives than in the other forms. When you have higher derivatives, you require certain strong conditions on the variables involved. You say that it has to be differentiable twice, differentiable 4 times. In the case of a beam, if you recall, let us go back a few slides. You look at this W over here, we are taking 4 derivatives due to the 4 W by dx to the 4. That means that this W has to be differentiable 4 times. Okay. Whereas, if you look at the potential energy, you have only d square W dx square only twice, and if you look at the third method, that is also only twice. So, as opposed to the weaker conditions of lower equilibrium, which we call the weak form, here we have it in strong form. And you need to have boundary conditions also along with that when you are doing force and moment balance, whereas those boundary conditions will come as part of the solution in the other 2 methods, that is the principle of minimum potential energy as well as principle of virtual work. Okay. The weak and strong once again are a matter of the order of the derivatives that exist in the expressions involved. In order to understand the 3 methods, let us take the simplest problem that one can imagine in elasticity, which is basically a spring of spring constant K, and we apply a force F and it is going to undergo a displacement delta. Everybody knows answer for this is that delta that we have or x that we have at equilibrium is F divided by that K. So, basically if I call this delta an unknown x, this is what you have, that is basically balancing force. Force, external force F is equal to internal force applied by the spring. When you pull it, it tries to pull you back, that is Kx. Is a force balance, internal force equal to external force. That is what is the method 1 that we saw in the case of a beam. Now, method 2 is a minimization of the potential energy. So, potential energy if you recall is strain energy, that is half k x square when there is displacement x of the spring, and then there is negative of the work done by the external forces, which you call work potential, that is F times x. Okay. That is a potential energy. When you minimize it, you take derivative of that with respect to x, that gives you half k x square gives you k x, and minus f x gives you minus f, goes other side you get k x equal to f, which is same as what we had with the force balance. Here we did not do force balance really, we rather minimize potential energy, which is equivalent to balancing the forces for the necessary condition of minimizing potential energy. This is what is method 2, which we saw for the case of a beam in the by using unknown function Wx. Now, there is method 3, which is the principle of virtual work. What we do is we already know that Kx equal to F, there is internal force, external force are balanced. Now, we imagine that this spring has a little, let us say it has come here, but as it moves a little bit this side, okay, that is delta x. So, after already from here to here we have x, right. Now, we move by additional amount, which is delta x. This additional delta x that is from here to here is purely imaginary, that is it is not real, it is virtual, that is the thing. So, what does the principle of virtual work say? It says that internal virtual work is equal to external virtual work. There is already F, we imagine that there is delta x, the external force does external virtual work F times delta x, and the internal force Kx does Kx times delta x. This is what it does. Now, delta x is arbitrary, okay, delta x is arbitrary, that is you can imagine any displacement that you wish, and for all of that this should be this should hold good. That gives you again Kx equal to F, because if it is arbitrary then Kx must be equal to F, and that gives you the same thing, right. So, the 3 methods give you the same equation which you can use to solve. Method 1 force and moment balance, method 2 minimum potential energy, method 2 the principle of virtual work. Now, we considered a beam and then we considered a simple spring to understand the 3 methods. Now, we can jump to make a general elastic body. Let us say I take the continuum mechanics potato fixed some place, and there are some boundary forces which are called tractions. There could be body forces such as gravity or centrifugal force and so forth for a 3D body, okay, continuum. Okay. It is not a beam or plate abstraction. For that, for those of you who are familiar with the notation, this is the differential equation, okay, where del dot we have D, which is the stress strain matrix, and then we have the strain. So, D basically gives you stress when you multiply with strain. Okay. In the tensor notation, we put this way D colon epsilon, that gives you stress together, and divergence of stress del dot sigma plus the body force such as gravity, centrifugal force and so forth, which act at every point in the body, that is a force equilibrium. Okay. If you were to take a differentially small element, a little cube here, I am drawing a very big cube here, but imagine this cube to be as small as one can imagine, and then look at various forces that act. What are the forces? External forces B that acts on it, and then you have stresses multiplied by corresponding areas over which, let us say you take the stress acting on it, normal and shear stress, what total force will be there. Likewise, on all the 6 faces of the cube, when you balance it out, you get this vector equation. There are 3 scalar equations here, okay, 3 scalar equations, because you have that many functions that you need to solve. That is, at every point there will be u, which is like a vector here, actually it is a vector, okay, and this will be the tensor, strain tensor. That u, when I put like a vector, what I really mean is that it has 3 components. Okay. There is ux, and then uy, and then uz. All of these will be functions of x, y, z, because we have taken a 3-dimensional system. If I say this is x, y and z. So, u that we have written here, that u is a function of ux is a function of x, y, z, and so is uy and so is uz. Okay. And in order to solve for the 3 unknown functions ux, uy, uz, you need 3 equations which are over here. That comes from the force equilibrium. Okay. If you take small cube and do the force equilibrium, that is what you get, and the strain is given by this expression for linear small strain, but the same holds for if you have a non-linear strain here, you can get a force equilibrium which will look like this, okay, with small changes in the stress and strain corresponding stress that you need to define. Okay. That is one way to do it for a general continuum. You can also do much simpler by simply minimizing potential energy, where the strain energy for the 3D body in tensor notation is written like that, and work potential of course is just body force vector dotted with displacement vector, that is that u that we have here is same as that. Okay. Minimize potential energy, it will find that vector function u with the 3 component ux, uy and uz. When you minimize with respect to these 3 the potential energy, you get back your differential equation. Or you can go to the method 3, where you can write the internal virtual work, which is given by this. This is internal virtual work, and this is the external virtual work. External virtual work, which I have indicated with 2 letters VW. So, this should be true for arbitrary virtual displacement. So, delta W, delta U here is the virtual displacement, that is imaginary displacement, consisting of 3 components. If U has ux, uy, uz, the delta U will have delta ux, delta uy, delta uz. Okay. So, even for a general elastic solid, you can write the static equilibrium in 3 different ways. Okay. And in mechanics, you can solve number of problems. One of them is, let us say, contact problem. Let us say I have a beam fixed on both sides, there is a loading, and below that there is a rigid structure. So, there is a rigid structure of certain shape. okay, rigid surface I can call it, rigid surface, that is this boundary. Okay. Now, there is load applied, this beam will deform and might contact this surface at different points depending on how much load you are applying, and then deform like this. Where the contact acts or contact happens, you do not know a priori, then what you do is to put a constraint, like the Chatterjee's problem, we had a constraint that curve has to lie below the river equation. Here we are trying to minimize the potential energy with respect to W of x, but we are also including a constraint that W of x should be less than G of x. Whatever W that we take, the gap that we have, G of x is here, it should be within that. Okay. The gap function is defined by the G of x here, your deformation cannot exceed the gap, that is what we have here as a contact constraint. Now, when you minimize it, you have to also put a constraint here like this, but that is a calculus variation because unknown is the W of x, okay, and the given loading Q of x and material property is known, second moment of area is known, and so forth. Okay. Now, we have an inequality constraint referring to the contact condition. Now, moving on to dynamics, we discussed the statics in mechanics. Now, mechanics also has dynamics where things are not at rest, they are moving. Okay. If we take a vibrating string, again the simplest problem one can think of in dynamics, a string that is kept taut between 2 points, let us say the spring length is L and the mass per unit length like mass density is denoted by rho, and there is a tension T here, then in order to find the dynamic equation which is shown here, okay, this basically comes by equating the forces that are acting when this is vibrating, it is free vibration, but there is going to be inertia force, that is rho W double dot. So, this dou square W by dou T square is W double dot. Okay. Rho W double dot is inertia force is equal to the stiffness force that is there, T into dou square W by dou x square. Okay. So, this is the force balance, but you can get it in a different way by using what is known as Hamilton's principle, where we have something called an action integral, which is denoted sometimes by A, sometimes by H, where there is a functional. If you notice, this functional has two variables x and t. We are integrated with respect to x and t because our function W here is a function of x and t. So, we have an extremized functional in two variables x and t, which is given as rho W dot square minus T W prime square, integrated from 0 to L over the space and T1 to T2 over time. If you extremize it, again notice the word that we are not saying it is minimum or maximum, we are just saying we are extremizing, we are getting optimal, but we do not insist on that being a minimum or a maximum. Okay. When you extremize this functional, you get back the equation that you would get when you do force balance, inertia forces brought in here along with the stiffness forces and damping you may have, and that is called the Hamilton's principle. So, Wxt which this vibrating string takes, it takes that particular shape which extremizes this functional, that is what this Hamilton principle says. And this is very analytical because you do not have diagrams anymore, in fact you do not need diagrams, we just write down strain energy, potential energy, kinetic energy, all of those energies and write this functional and say extremize it to find Wxt function, and you get the differential equation to solve for. In the case of a beam, if you earlier we had only these two terms, now we have the inertia force also, rho into W double dot or d square W by dt square. Okay. What is the function that we minimize or extremize there? In addition to what we had earlier, that is the strain energy and the work potential, now we have kinetic energy also. Okay. So, here what we have inside what we have 0 to L and T1 to T2. What we have inside, actually there is a name for it called Lagrangian. Okay. This L is called Lagrangian. This another kind of Lagrangian optimization, we will come to that later. For now, this Lagrangian is kinetic energy minus potential energy. Okay. So, this Ke is kinetic energy. Okay. Potential energy we have already discussed, but notice that it is kinetic energy minus potential energy. That is what we have. That is why potential energy minus, and this was minus of minus, that is why it became plus. Here we have kinetic energy. So, this Lagrangian, if we take integral over space, okay, and time. So, L itself will have the time part of it here. This L that we write that involves already, in fact, I need not write this here, because L, the way we write, it will already include this integral over space. Okay. That is L. What I have encircled now is your Lagrangian, and then this T1 to T2 L dt is what is this action integral, or what we call the Hamiltonian sometimes, right. If you extremize this action integral with respect to W x t, then you get the equation of dynamic equilibrium, or what we call Newton's second law. Okay. So, now to summarize one more time, we have force balance and Newton's second law, we have principle of virtual work, and we have not discussed this D'Alembert principle in the framework of alpha variation. This is the intermediate result which we will see later. Okay. And we discussed static case minimum potential principle, and then Hamilton's principle, which says we have to extremize what is called an action integral, which is T1 to T2 L dt, where L is kinetic energy minus potential energy, and is called Lagrangian. Okay. Now, moving on to design or structural optimization. Okay, structural optimization is structural design. Right. In this class, we are focusing on mechanics as well as design using variational methods. Okay. When you think of a structure, there are a number of things that we might want to optimize for. You want to minimize the weight or volume of material or cost, and stiffness you want to maximize most of the time. You definitely want to maximize strength. Sometimes you want to have flexibility of to some extent, and you definitely want your structures to be stable. For dynamic considerations, natural frequency, mode shape will be there, all of these things you have, and you have to define your variables. Okay. The variables which define the geometry of your structure. Okay. All of these can also be posed as calculus variation problems. We will look at a few examples now. Here is a problem of minimize the strain energy of a beam with an upper bound on the volume of material. That is, you are given a beam, let us say of rectangular cross section. So, if I take a beam of rectangular cross section, let us say width is b and depth is d. Okay. This is our rectangular cross section, and if I integrate rectangular cross section 0 to L, we are not saying that even though it is rectangular cross section, the b and d here, okay, this is the d, b and d are not the same along the beam. So, it can vary. Okay. The sometimes cross section profile can be small, and sometimes can be very large, and then small again, and so forth. Okay. So, if I integrate that BD over the distance 0 to L, that gives you the volume that should be less than or equal to that V star that is given. You are given certain amount of material, volume of material, that is your resource. Within that, you have to distribute along the length 0 to L. Sometimes you can make it bigger area of cross section, smaller cross section, and so forth. You change it, and you can use either B or D. In this case, we have used B of x that is the width profile of the beam as a variable, we want to minimize the strain energy to make the stiffest beam, and the strain energy is written here in terms of EI. You recognize for rectangular cross section B dq by 12 is second moment of area are called I, and then d square w by dx square whole square will be involved in this strain energy expression, and then W that we use here, it has to be satisfied by it has satisfied a governing equation which is equilibrium equation, which is written there, and then you have volume constraint and length is given, loading Q of x is given, D is given, depth of the beam, and then V star, and V star is a volume, that is a load, upper bound on the volume material that you can use, and the Young's modulus. Okay. So, with all this data you have to solve this problem. As you can see, it is a calculus variation problem because we have a functional which is an integral, and there is a differential equation constraint, another functional constraint here on the volume of material. Let us say you want to worry about strength, then you want to minimize the maximum stress that is there in a beam, then you would say minimize maximum stress, maximum over x, that is 0 to L that you have the beam, anywhere the maximum stress can be reached depending on the load and boundary condition. Now, you want to minimize that maximum stress by adjusting the B of x, which is the width profile here. Okay. Then again we have the a functional. Now, if you look at this, this is also a functional, it is not an integral, it is not an integral now, but it is a functional nevertheless. Okay. So, in this lecture you have to focus on the types of functionals, that is a different type of functional, maximum over the spatial domain, a quantity, in this case it is stress, and then there is a governing equation and there is a resource constraint in the form of an integral. Let us consider a even more complicated problem where we are considering electrical domain, thermal domain, and then elastic or compliant, okay, elastic or compliant domain, an actuator, electrothermal compliant actuator. So, there we like to minimize minus u out is output displacement. When I put minimize minus u out, I am basically maximizing the output displacement, which is what we want to do when we have an actuator. We want to maximize the stroke of the actuator, and there is a variable, we do not have to worry about what that variable stands for now, just rho x y for a 2D problem. There are these governing equations, electrical, this one is for electrical, and this is for thermal, this is for elastic. So, this is for electrical, this is for thermal, and this is for elastic analysis. Okay. And there is a volume constraint like before. This is also calculus variation problem. Now, if you see, this is also a functional, that is displacement at a particular point, functional can be just that also. Okay. Let us look at the features of calculus variation problem before we end this lecture. So, it can be just an integral, it can be, we have not considered that, but it can be ratio of two integrals, it can be integral with another integral which we came across in the case of optimal control, the helicopter problem, and it can be maximum minimum of a function that we considered in the case of minimizing maximum stress in a structure. So, by looking at all these examples, we know how a functional looks like now. In the next lectures, in the subsequent lectures, we will look at the nature of the functional in a little bit more detail from the mathematical viewpoint. Now, to summarize this lecture, we have considered a number of problems both in geometry as well as in mechanics and formulated them based on what needs to be minimized and what needs to be probably maximized instead of minimized, then we put a negative sign. And then we also looked at constraints, they can be constraint like a differential equation form, or they can be integral form, or just at one point. Okay. And again the nature of the functional, a number of ways, just an integral or integrals and integrals, ratio of two integrals which you did not see today, min or maximum function, and it can depend on one function or more than one function. Like if you do 3D elasticity, you have ux, uy, uz, 3 functions that are unknowns, and it can dynamics case it can depend on space and time variables. And most important thing for this lecture that you need to remember is that there are 3 different ways to pose the static and dynamic equilibrium problems in mechanics, and 2 of them are related to variational methods. which is the topic of our course. Thank you.